All right, so what we're looking at next is the second derivative, or we could say higher order derivatives, because we could have a second derivative or a third derivative or a fourth derivative. We could keep going all day if we wanted. But basically the nice thing about this is it isn't a really, really difficult concept, because the second derivative is simply taking the derivative of the derivative. Okay, so as you can see here, we have our notation for the first derivative. If y is f of x, then the derivative of y with respect to x is the same as y prime, or f prime of x. That's all notation referring to the first derivative that we're used to using. Okay? If I take, notice the notation here, if I take the derivative of the derivative, I'm taking, we use the notation here, d squared y dx squared, okay? That's the same notation as y double prime, or f double prime of x. That's our second derivative, okay? Now, we don't just keep putting primes if we go higher than the second derivative. If we go higher than the second derivative, we just put the number of which derivative we're dealing with in little parentheses next to the f or next to the y. And we put it in parentheses just to make sure we don't confuse it for an exponent. Okay? So, for example, I have a polynomial down here, and we could take, obviously, the derivative, f of x, is 15x squared plus 14x minus 5. But then I could go one step further. I could take the second derivative. And to take the second derivative, I'm just taking the derivative of 15x squared plus 14x minus 5. So now I have 30x plus 14. All the rules for taking the derivative are the same. Product rule, chain rule, quotient rule, all the other rules that we've learned, they're all the same. So we're not doing anything new, we're just now doing it twice. Okay? Or if we wanted, we could go a step further and we could do a third derivative. So I would put like the little 3 there. The third derivative of f of x would be just 30. And if I wanted, I could take the fourth derivative and it would equal 0. Okay? But that's all we're doing here. And the applications, as we'll see, we're able to use, especially the second derivative, is the main one that we're actually going to use, allows us to figure out a lot of different things about motion or about the change of something. Okay? So before we actually do one, I want to look at and just get the concept down here, okay? We said the derivative is the slope of the tangent line. In other words, it is the what? Well, slope is velocity, okay? Slope we could say is velocity or rate of change, right? Now, think about this. If I'm taking the derivative of the derivative, I'm finding the rate of change of the velocity. So if my velocity is changing, what do we call that?
Acceleration.
That's the acceleration. Okay? And that acceleration, if it's moving in the positive direction, or if it's pushing in the positive direction, it's going to be a positive acceleration. If it's pushing in the negative direction, it's going to be a negative acceleration. But that's a concept there that we're going to be using quite a bit, is that idea of acceleration. Okay? Now, in terms of, that's thinking about it in terms of motion. In terms of the graph, our derivative determined whether we were increasing or decreasing. The second derivative is going to determine what we call concavity. And we'll define that more next time we meet. All right, but we have concavity. Now, let's actually try one of these, okay? We're going to find the second derivative for tangent of x cubed. Okay? Tangent of x cubed. So, obviously, to find the second derivative, I first have to find the first derivative. Okay? So, I'm going to find dy dx. And does anyone remember what the derivative of tangent is? Very good, secant squared. So in this case, it would be secant squared of x cubed.
Times 3x squared.
Very good. Chain rule times 3x squared. Okay? So that's our first derivative. If I want to take the derivative of that derivative, what am I going to have to do? The product rule. Okay? I will say one of the most common things that students forget about is to actually use those rules on the second derivative. Because we didn't have to use the product rule on the original function, but now we do. Alright? It's really easy to just jump to conclusions and say, oh, it's 6x times whatever secant squared is. And it's a little more complicated than that. Alright? So, let's work through the product rule. Okay? U is 3x squared. V is secant squared of x cubed. So we've got a double chain rule there that we're going to have to work with. And there's a couple of ways you could handle that. Alright? Get the easy part out of the way here. That's going to be 6x. Does anyone happen to recall what the derivative of secant is? Okay. What? What?
1 over negative sign.
That's not a bad thought, okay? It's not a bad thought, because cosine is negative sign, but actually you brought up a point, you brought up something, though, that we could use, okay? We know secant's negative sign. Or secant's negative, stop. Cosine is a derivative of negative sign. Secant is 1 over cosine, right? So how could we rewrite V?
1 over cosine squared.
Uh-huh. We could rewrite this as 1 over cosine squared. Or, since we're going to do derivative, how about cosine to the negative 2 of x cubed?
Are they gonna give us questions like that?
So we definitely have to know these derivatives.
Well, here's the thing. Actually, IB does not require you to know anything except for sine and cosine.
Oh, okay, cool.
Now, if they asked you for derivative of tangent, they would expect you to use the quotient rule and your trig identities if you didn't know it. If you do know it, then it saves you a lot of work. Okay?
You're gonna take off points though? If you just say like
No,
derivative of tangent is secant.
no. Not unless they said prove that, this is the case or something like that. Alright, so now that we have it rewritten, we can find V prime. So like we said, we've got a double chain rule going on because we have something to the negative 2 power. So what's the derivative of something to the negative 2 power?
Negative 2 times the negative third.
Good, negative 2 times something, in this case cosine of x cubed, to the negative third. And notice that x cubed stays put. Alright, we need more. We've got the chain in a chain here, so now what?
Times 3x squared.
Times a 3x squared. I'm going to put that at the end because that's actually the innermost function. What's that middle function we got to take the derivative of too?
Cosine.
The cosine. What's the derivative of cosine?
Negative sign.
Negative sine. So we have a negative sine of x cubed, and then times the derivative of x cubed. Alright? So we've got a chain within a chain. A couple links in our chain. So now I would go ahead and simplify a little bit here. I have a negative and a negative, so that's a positive 6x squared times sine of x cubed. And since that cosine is to the negative power, I'm going to go ahead and put it in the bottom as a cosine cubed of x cubed in my denominator. Okay?
Wait, is it sine of x cubed?
It's sine of x cubed, yes. When you have these trig functions, what's inside the trig function is not going to change the whole way through. Okay? So. Alright, so now we have everything that we need in order to get our, in order to use our product rule. Okay? So let's start doing that. We've got u prime times v. Well, v was the secant squared, or I'm going to use the 1 over cosine squared since my v prime has the over cosine cubed. Alright? So this times 1 over cosine squared of x cubed. So that's my u prime v. Plus u 3x squared times v prime. Well, we know v prime is 6x squared times sine of x cubed over cosine cubed of x cubed. Alright? Everyone with me so far? Notice we're getting a lot of good practice here with our rules from our last unit anyways, so it's all building on itself and we're getting lots of practice. And one thing you'll find is as we do second derivatives, if it was a polynomial to begin with, we saw it got really, really easy the further we went. With other functions, however, it typically gets more complex. Okay? So at this point, I'm just going to simplify a little bit of this, all right? I see that I have a 6x in both numerators. I also have a cosine squared of x cubed in both denominators. So I'm going to factor that out, and I get a 1 plus, there would be a 3x cubed sine of x cubed over cosine of x cubed. Notice the cosines to the first now because I took out 2 of those. Okay?
So you took out completely the 6x cosine squared.
Yeah. Now, real quickly here, I just want to show you something. We already saw that 1 over cosine squared was secant squared. Okay? So I could have rewritten this as 6x times secant squared of x cubed times 1 plus, and then what's sine over cosine? Tangent. So I could rewrite this as 3x cubed times tangent of x cubed. And the reason why I point that out is because if you happen to remember, the derivative of secant secant, is secant times tangent. You see the secants and tangents in there? If I had used secant times tangent instead of converting secant into 1 over cosine, I would have gotten this more directly. Okay? I just had to remember a little bit more. Okay?
Wait,
So.
secant x equals to secant x times tangent x?
Yes.
Like by which property?
You don't have to know that. That's another derivative rule. Just like derivative of sine is cosine, derivative of secant is secant times tangent. Okay? Alright, so what's our second derivative used for? What does it tell us about our function? It actually tells us what's known as the concavity. Alright? Sometimes you'll hear this described as the curvature. Alright? The curvature of our function, or the concavity of the function. Alright? Now, concavity can be a little bit of a nebulous kind of concept. So I really want to try to help you wrap your heads around this and make sure you understand here. First of all, just mathematically speaking, we use the second derivative to determine concavity because when our second derivative is negative, we say the shape is going to be concave downwards. Okay? What makes this a little bit tricky is that you don't always necessarily see the whole downward arch, okay? For example, you have a logarithmic function that looks like this, and it continues to increase forever. However, it's concave downward forever, okay? And you say, well, it never quite goes down, and yeah, you're right, it never does go down, but that's a matter of the first derivative, not the second derivative. Okay? The concavity is downward for that. Okay? We'll look at that a little bit more in a sec. The second derivative is positive when it is concave up. Alright? And you see there the basic shape of concave up, but again, we could have, say, an exponential growth function, all right, like this, where we know that that is increasing forever, but that's also concave up forever, okay? Now, you might say, well, what is concavity, or what does the second derivative really tell us, all right? Well, remember, derivatives give a rate of change, okay? So, f prime, we already know, is the rate of change in position. The rate of change of position is also known as velocity, okay? So this is velocity. This is how we can have a negative and positive, because the negative simply tells us that we're moving downward, and the positive tells us we're moving upward. That's how we tell things are increasing and decreasing using our first derivative, okay? The second derivative is the rate of change of the velocity, which we briefly mentioned earlier gives us the acceleration. How is the velocity changing? That is our acceleration. Are we speeding up? Are we slowing down in a particular direction? Okay? I sometimes describe it this way. The velocity is telling us which direction we're going. The acceleration is kind of telling us which direction we're trying to go. If you think of it like if you're slowing down, you're kind of trying to go the opposite direction. And eventually, that trying to go the opposite direction will slow you down so much that you stop and then you actually start going the opposite direction. Okay? Your acceleration hasn't changed. You're still pushing backwards the whole way. But it's just a matter of, what way you were kind of trying to go. If we look here on the left, we have this concave downwards curve. You can see the tangent lines that are drawn there. And you'll notice that as we go from left to right, our slope of a tangent line is going from 2 to 1 to 0 to -1 to -2. So our derivative is doing what?
Decreasing.
Decreasing, okay? It's decreasing. Okay? Now notice we're not talking about the function, we're talking about what's happening to the derivative. The derivative is decreasing. Therefore, our second derivative must be not necessarily decreasing, but it must be
Increasing? No, not
Downwards?
Decreasing slowly.
let's think about this. If our velocity is decreasing, our acceleration must be
Increasing? Decreasing. Concave down?
positive or negative?
Negative.
Negative. Okay? Our acceleration must be negative. If you think about it this way, all right? This is decreasing from 2 to 1 to 0 to -1 to -2. Okay? So as that decreases, the rate of change of the velocity is negative. Okay? And in fact, if we were to graph this, let's think about this. If we were to graph this, the slope is a +2, then it's 1, then it's -1, then it's -2. The actual graph of the derivative here would look like this. Okay? I missed one. Does that make sense? Okay? So you can now see that is, if that's our derivative, and this was our original function, okay, the derivative is decreasing because its slope is negative. Okay? So the second derivative is negative. Okay? And that's why this thing is concave downward. Right? Yes?
I'm sorry, why is that the derivative? Like is that's the derivative for when? That line.
For all values of x, okay? See, if we made, okay, this is the line y equals x squared, so we know it hits the origin, right? And it goes downwards. It's the parent function flipped across the x-axis. So that's our graph. And here's 1, 1, okay? My points aren't exactly right, but okay, there's the point 1, -1. My slope is a -1 at that point. Okay?
Okay.
At the point well, here the slope is a -2, okay? So I'm at -2 on my derivative at that same level. Okay? So here I've graphed the derivative function on the same coordinate plane as the actual function. So you can see the derivative is decreasing over the whole path of the function in this case.
Okay.
Okay? Now, on the right side here, our derivative is actually changing from -2 to -1 to 0 to 1 to 2. So the derivative is increasing, which means my second derivative must be positive. Okay? There is a positive rate of change in my velocity. Okay?
But
if like the first derivative is decreasing, can the second derivative be positive? Or no?
If the first derivative is decreasing?
Yeah.
No, that would mean if your first derivative is decreasing, then that means you have a negative acceleration, negative second derivative, okay? Don't confuse that with what the function itself is doing. I know that my function is increasing here and decreasing here. That's not what we're talking about. We're talking about what the derivative, which is our slope, what it is doing. It's changing from 2 to 1 to 0 to -1 to -2. Okay? We are going to look more tomorrow at looking at these graphs side by side and picking out different features. Okay, here's the graph of the second derivative. What can we tell about the first derivative from that? And then once we see a graph of the first derivative, okay, what can we tell about the original function from that? And we're going to look tomorrow at how all that kind of ties together. Okay? Now, what we're looking at here is what's known as a point of inflection. Okay? A point of inflection is a change. It's a point where we change from being concave up to being concave down, or vice versa. Okay? It's a change in curvature. Now, we looked at the change from increasing to decreasing, or vice versa, with our first derivative. Well, that's how we got max and min points on the function itself. And we did that by finding those critical values, setting the first derivative equal to 0. Okay? Well, here, we're going to look at when our velocity changes from negative to positive or positive to negative by seeing when does the second derivative equal 0. Okay? If you notice here, for this part of my function, we are concave down. Okay, concave down. So that means my second derivative is negative, right? Well, over here, once we get past this, you can see it's starting to move towards the increase. It's still going down here, but it's going down slower. All right? It's trying to go up, you could say, until it finally hits this min point, and then it actually does start going up. Okay? So there, we're concave up. And that's because the second derivative is positive. Okay? Oops. It's positive. That point of inflection is obviously the point between those, and that's where our second derivative equals 0. Okay? Yes?
So is the point of inflection always on the x-axis?
No.
No.
No. For some functions it
because
is.
it's, okay, never mind. Because it's f of x, okay.
Yeah, it's where the second derivative
Function,
equals
yeah.
0, not the original function. Now, we've actually seen one special case of this already happen. You remember what we would call this kind of a point right here?
Plateau point.
Yeah, that's a plateau point. Now, something important that you see here. A plateau point was when the first derivative equaled 0, but there was no sign change. Notice we're decreasing here and we continue to decrease. That was our plateau point. Another way you can tell it's a plateau point is by seeing that the first derivative equals 0, but also the second derivative equals 0. Okay? So, and f double prime of x equals 0. Okay?
You could like a spy name.
What?
You could like a spy name. Double prime.
Double prime?
Do you see it? Double prime.
Now, here's one thing that's important to recognize. All plateau points will be points of inflection. The converse of that is not true. Okay? Not all points of inflection are plateau points. You can see right here, there's no plateau on the left-hand side here. It just goes straight through it, but that's where we stop speeding up and we start slowing down. Okay?
So not all points of inflection are plateau points, but all plateau points are points of inflection.
That's exactly right. Yes. Okay? So you could see, here's our points of inflection, or POIs, and a subset of those are the plateau points. Okay? All right. So, got a little bit of practice here for finding when these equal 0, and then we'll do application tomorrow. Okay? All right. Have a great day, guys.